Welcome back. We are still talking area under a curve and we're looking at definite integrals packet page 10. I just wanted to real quick wrap things up talking about examples 5, 6, and 7. And check out 5 and 6 first. Again, mysterious type of question. You're given not the equation of f of x, but little tidbits about some of its definite integration here. From 0 to 5, the area is 10. And from 5 to 7, the definite integral is going to be 3. Does that help you answer these questions? Let's go through one by one. Part A says, do you have enough info to get the definite integral from 0 all the way to 7? Well, you do. There's a rule with subdivisions that you can add up the integral from 0 to 5, which was 10, plus the next chunk, the integral from 5 to 7. Add that to 3. So those two together give you the entire integral from 0 to 7, 13. How about B? Look at the subtle difference in part B, right? This time, this is the rare case where you see the bigger value coming to the bottom and the smaller one at the top. Well, if the integral from 0 to 5 is 10, integration rules say that the integral from 5 to 0 is the opposite sign of this answer. So this answer gets to be negative 10 by definition. Okay. This one, we've never seen one like C. Integral from 5 to 5. So get this. They want you to find the area under the curve of not a whole interval, just at the x value 5. There is no area here. You have a 0 area every single time. And again, this is rare to see, but if you ever see the same number on bottom and top of that integral, there is no area to be found under that curve. It's just going to be 0. Can we solve the last one? D says integral from 0 to 5, which we have, but not of f of x of triple f of x. Well, rule says easy enough. You can just take its integral, 10, and triple the 10. Leave the constant in your answer, and you get 30. 6 is very similar. I would encourage you to pause the video, try 6 on your own, and then tune back in so you can see if our answers match up. Okay, well, I'm dying to try it. You know the integral from 2 to 6 is going to be 10, and you know the integral from 2 to 6 of g of x, a different function, is going to be negative 2. Integration rules say if you want the integral from 2 to 6 of the sum of the two functions, you can separately add their two integral values. So you can add 10 plus 2, or plus negative 2, I should say, gives you a total of 8 for part A. So that's pretty cool. What if you subtracted g of x minus f of x with the same limits of integration that you have all over the place? G of x is negative 2. I'm subtracting f of x's integral, which was 10. Negative 2 minus 10 gives you an area of negative 12 there. How about the next one? Integral from 2 to 6, so same limits, of 2 times g of x. Well, you know g of x's integral in that region is going to be negative 2. I need to double it because of that constant out front. So 2 times negative 2 gives you negative 4 as an answer for C. And then what do you think for D? 3 times f of x, same interval here. Well, f of x was 10. So we'll triple it, and just like we got in part D of the last one, a 30 for that answer. So don't be scared off from problems like these just because you're not given a ton of info about the integral. Sometimes it's a little more common sense and a little easier that you can see things like, oh, integral of the sum is just going to be the sum of the two definite integral values. Last but not least, number 7. We had to get to this one. I've been thinking about this problem, and it's because it ties in. This is a really good review question of a lot of integration skills that we've been going over since the start of this unit. And there's more involved in this question too. If I'm looking at it, I see it's a definite integral from 1 to 2. I could probably use a calculator to graph it, but I don't have to at this point in time. But check it out. This is going to be tougher to integrate. I noticed some inside-outside stuff going on. This is going to require, wait, is that Soldier Boy I hear? Is he saying, you substitution? I knew I would get a chance to make that joke again. So let u equal something. Now's as good a time as any to just refresh this topic. Are you going to make it sine of x? Are you going to make it cosine of x? I wouldn't make it sine of x cubed. Remember, we picked the innermost part of the function. Let's go with just plain old sine of x for 2 reasons. It is not more complicated than cosine, so that's not a reason. There's 2 other reasons. Reason 1, it's more innermost, right? Because you're having sine and it's raised to the 3rd power. Reason number 2 is that its derivative appears. Its derivative is going to be cosine. So speaking of derivatives, the side work for u substitution was to take a derivative here, find a du dx, and that is cosine of x. Then we got du by itself. That was usually our strategy so that we could get this whole problem in terms of u. So du equals cosine of x dx and du over cosine of x. Man, I missed u substitution, let me tell you. This and this are your puzzle pieces to plug back into the original. Let's see how well this is going to work out for us. Integral from 1 to 2 of u to the third, because that's what you called u, was sine of x. Cosine of x that we really need to get rid of. That's going to be problematic if that doesn't go away, but lo and behold, it will, because instead of writing dx, we're writing du over cosine of x. Beautiful. All the x's should go away. Get rid of those, and you're just integrating, taking the definite integral from 1 to 2 of u cubed du. We've seen this on at least another homework assignment where u substitution snuck its way into this packet. The thing to be careful of is to remember that these limits of integration are x values. They're not u values. It might help to actually write x equals 2 and x equals 1 just to remind yourself to remember to sub back in. So let's give this a try. We're taking the integral of u cubed, so it'd be 1/4 u to the fourth. Instead of writing a plus c, we want to evaluate this from, I'm going to be even more careful and write x equals 1 to x equals 2. And then before I start plugging back in, let's sub back in for x. So u was what we called sine of x to the fourth over 4. Now, something I would caution you about. We are evaluating this from 1 to 2, and this is going to be a weird looking decimal, so I am going to use the calculator. However, I don't see degree signs after either of these. So I want you to write to yourself, watch out. Achtung, as they would say in German, watch out. These values, 2 and 1, I'm going to say these are radian values, not degree values. Because we're about to type a sine, a trig function, into our calculator, you always have to be cognizant of your mode. And if you don't see degree values here, you have to assume that we're working in radians. So I'm going to do that first before I type this in. Let me pause while I grab the calculator. There we go, much better. Got the calculator. I'm going to go mode, make sure I'm in radian and not degree mode. That looks pretty good. I'll quit out of it, and then I want sine. Let's write what we want to type. We want to plug in the 2 first. So sine of 2 radians to the fourth over 4 minus sine of 1 to the fourth over 4. That's exactly how it should be typed in. So let's show that here. We've got, now that we're in radian mode, sine of 2 and raised to the fourth. And maybe I'll put that whole thing in parentheses. So on second thought, parentheses, sine of 2, close the parentheses twice, raised to the fourth. So raised to the fourth. And we want that whole thing divided by 4. And now I'm going to subtract, so minus sine of 1 to the fourth. So parentheses, sine of 1 radian, close it twice, to the fourth, divided by 4. And if it's all typed in correctly, we get about 0.456, kind of like we're counting. So about 0.0, I should say, 456. If we were to graph this, we would see there's very little area under the curve from 1 to 2 under that trig function. Okay, catch you next time. Have a great day.